In this video, we're going to look at homogeneous systems of equations and rank. So a homogeneous system of equations is simply a system of equations in which all of the equations are equal to 0. They're all the same, they're all equal to 0. That's the only thing that makes it a homogeneous system. If they're not equal to 0, we call it non-homogeneous. So let's take a look at this system. If we were to write it as an augmented matrix, notice that the right-hand column, the augmented part, would all be zeros as well. And if we were to look at this system, one thing you'll notice is that it's always going to have a solution. It's going to have a solution where each of the variables is equal to 0. Because if each of the variables were equal to 0, we would of course get 0 out. This is called the trivial solution because it's kind of obvious and not particularly exciting, but it is something that a homogeneous system of equations will always have. So one of the questions we often want to ask is there a non-trivial solution? So let's see if we can find the non-trivial solutions to this system. And so as per usual, the first thing we'll do is we'll write it as an augmented matrix. And then we'll row reduce it. And in this case, it reduces down to what you see here. So notice that in this reduced echelon form matrix here, that we have 2 rows with a non-zero leading entry, which means we have 2 pivot positions. Now the variables corresponding to those columns, in this case x1 and x3, we call these basic variables. So the variables corresponding with pivot positions are called basic variables. And then the other variables, x2 and x4 in this case, are called free variables because they are are free to be whatever they want to be, basically. And then x1 and x3 are determined based on the values of x2 and x4. So to write the general solution here, what we'll typically do is parameterize it. So we're going to let each of the free variables equal a parameter and then express the solution in terms of those parameters. So in this case, x2 will let equal some parameter s, and we'll let x4 equal some parameter t. And then we can express x1 and x3 in terms of those. So if we were to look at our top equation, we have x1 plus 2x2 plus 3x4 equals 0, as we see here. And then if we solve this for x1, we get x1 equals negative 2x2 minus 3x4. And then using our parameters here, we can rewrite that as 2s minus 3t. From the second line, we got x3 plus 4x4 equals 0, or in other words, x3 equals negative 4x4. Again, using our parameters, that would be negative 4t. So if we take these 2 equations here along with the top 2 that we had there, we get these 4 equations as our basic solutions, and these describe x1 through x4 in terms of our 2 parameters s and t. Now one thing that's kind of interesting we can do here is we can group these together in a way by taking everything that involves s and multiplying it by a column vector, and everything that involves t and multiplying it by a column vector, and then sticking our variables in a column vector. And you'll see that our vector of solutions then is written as the parameter s times this vector plus the parameter t times this vector. And because we can write it this way, these 2 columns, the negative 2, 1, 0, 0, and the negative 3, 0, negative 4, 1, these are called basic solutions. And you'll notice that any solution then is written as a constant multiple of the first basic solution plus a constant multiple of the second basic solution. And this idea is so common that it gets a special name called a linear combination. So when we write the solution like the solution vector equals s times the first basic solution plus t times the second basic solution, we're expressing the solution as what's called a linear combination of the column vectors. So a linear combination simply means that if we have a bunch of vectors, that we can find scalars, in this case a1 through an, so that the vector x is written as a constant or a scalar times the first vector plus a scalar times the second vector, all up to a scalar times the last vector. And just to be clear, some of these scalars could be 0, so it would be x would still be considered a linear combination even if it was just, let's say, 2v1, or if it was just a combination of two of the vectors. But this is the idea of a linear combination. So this gives us an idea of how homogeneous equations are solved. How does this relate to solving a non-homogeneous system? So it turns out that if we were to solve a non-homogeneous system, the resulting solutions can be written as a particular solution, so some other solution, plus a linear combination of the same basic solutions that we got out of the homogeneous system. So let's take a look at that. So here's the same left-hand side, but now we have non-zero right-hand side. And if we were to row reduce this, it reduces down to here. And then we could parameterize the solutions the same way we did before. And you'll notice what we end up with here is this part here, the s times this vector plus t times this vector, is the same that we saw with the homogeneous system. The only difference is this extra part here. And so this extra vector here, the 3, 0, 2, 0, is what we call the particular solution. And then these other two vectors form the basic solution. And again, those are the same basic solutions that the homogeneous system had. So changing the right-hand side only changes the particular solution. The basic solutions always stay the same. So let's talk now about another concept called rank that is related to what we've been doing here. So rank is, by definition, just the number of leading entries in the echelon form of the matrix, and is denoted rank of A. And notice, since it's the number of leading entries in the echelon form, that means it's also the number of pivot positions and also the number of basic variables. So let's look at an example. Looking at our matrix from earlier, this matrix reduced down to this, and we noted earlier that there were 2 pivot positions. And because it has 2 pivot positions, the rank of this matrix is 2. And again, that's referring to the rank of the original matrix here. Again, it's based on the pivot positions of the reduced matrix. Okay, so how does rank relate to the solutions that we get? Well, let's say that A is an m by n coefficient matrix. So it's just the coefficients. It does not include the right-hand side. For a system of equations, and suppose that the rank of the matrix is R. So if R is equal to n, that means the rank is the same as the number of columns of the matrix. In other words, the rank is equal to the number of variables. That would mean that every variable is in a pivot position, so every variable is a basic variable. There's going to be no free variables. That means we're going to have only one solution. Or if there was a right-hand side, it's possible that there could be no solutions. If it's homogeneous, there will always be a solution and just one, the trivial. If it's non-homogeneous, it's possible that there's no solutions, or there's just going to be one unique solution. If, however, the rank is less than n, so the rank is less than the number of columns, that means that there's going to be variables that are not in a pivot position, and we will have free variables. And when we have a free variable, that means we're going to end up with one of those parameterized solution sets, and we're going to end up with infinitely many solutions. Or again, if it's a non-homogeneous case, it's possible that there could be no solutions as well. So the rank of a matrix gives us some useful information about the types of solutions that we might get out of the system.